Alrighty, we are now ready for lesson 4.8. We've been covering modeling. We're going to continue to cover modeling. And this time we're going to talk about something called sinusoidal modeling. Oh my goodness, that's quite the word. Okay, so basically we're going to model some periodic phenomena, things that repeat over and over again in a cycle. Okay, and those are going to be with equations involving sine and cosine. We're going to talk about real world problems. We'll do a little simple harmonic motion when you get to your worksheet. And we're going to talk about some regression capabilities. Okay, so we are ready to move forward. Here we go. Okay, two basic trig functions that you'll recall. Now these aren't written on your notes, but if you need to, go ahead and write them down. And those are the sine and the cosine curves. We should know the parent function points for those. The period of each of one of them is 2 pi, and the amplitude is, of course, 1. Okay? Now, you'll notice when we take sine and cosine, hopefully you've noticed by now, that they're almost the same two curves. Okay? What we can do is we can think of a cosine. If we take the sine curve, let's just trace this for a second, and we look at our sine curve rather, what we can do is we can notice that sine curve repeated inside of the cosine curve. Okay? So there it is. It's built inside of there. And it's really not much different than a sine curve. If we graph them right on top of each other, we'll notice all we got to do is take our cosine and move it over, or take our sine and move it over left, and we would have a cosine. Okay? So for the function f of x equals cosine of x, we can think of it as a sine curve. It just is a sine curve with a phase shift. How far? One little tick mark would be, you're not saying it out loud, pi over 2 to the left. Okay? I'm sorry. Yeah, pi over 2. Okay. So if we take a sine curve and we move it pi over 2 to the left, we would get a cosine curve. Okay. If that's the case, then really there's not much difference between a sine and a cosine, just the phase shift. And either shape can be based on a sine curve. And we're going to have a name for that. It's called a sinusoid. Okay? So a sinusoid is any function whose graph is a transformed sine curve. If I can take a sine somehow and manipulate it, stretch it, shrink it, slide it, move it around, and get the curve in question, then that curve is a sinusoid graph. Okay? So we won't distinguish a whole lot between sines and cosines unless the problem dictates it. We'll talk about that more in a minute. Okay, first example. We've got a Ferris wheel. And the Ferris wheel makes one complete turn every 20 seconds. We've got a rider's height above the ground. So here I am, I get on my Ferris wheel, and I start riding around it. Okay? It's going to complete one turn every 20 seconds. With these types of functions, what you want to watch for is how long for one cycle. However long for one cycle is going to talk to you about your period. Okay? So they were nice enough this time to go ahead and give us a model that they would like us to use. Okay? So we're going to apply that model to this problem situation. What is the value of A? Well, A in our model is simply our amplitude. In other words, if I start right here, how much higher will I go as I ride the Ferris wheel? And how much lower will I go? Well, I'm only going back and forth. I go up 25 feet, I go down 25 feet. Okay? So the value of A, my amplitude, is going to be 25 feet. Okay? All right. Second thing, we want to know the vertical shift. Okay? Well, the vertical shift is how far the middle of this graph is above the x-axis. Well, we know that this piece was 25 feet. And we know that at the bottom, we don't want to drag people's toes on the ground, so we have to have the Ferris wheel a little bit above the ground so nobody's feet drag for safety. And that bottom piece is 8 feet above the ground. So if my x-axis or my ground is down here, where is my vertical shift? Well, it's the 8 feet I got to go so I don't drag anybody's toes, and it's the 25 feet that I oscillate back and forth between. So 8 plus 25 is going to give us our value of k, which is 33 feet. Okay, that one's not quite obvious. Let me look at a picture. We got to think about it a little bit. All right, the value of W. Okay, now W is going to be the inside number. And if you look back at our model, this inside number is our horizontal stretch or compression. You might remember that as our period. They've already told us that it takes one complete cycle, completes one complete cycle in 20 seconds. So we know that the period is 20 seconds. But hopefully we remember from the graphing unit that just because the period is 20 seconds doesn't mean the number in the equation is 20 seconds. No, the number in the equation came from 2 pi divided by b. In this case, b is a w, okay? And that's the w that we're looking for. So 2 pi divided by that w is going to equal my 20 for my period. Okay, again, how am I going to solve this? Well, I'm going to multiply both sides by w. And then we're going to divide both sides. So now I have 2 pi equals 20w. I'm going to divide by 20. And I'm going to end up with w equaling 2 pi over 20, which would be 1 pi over 10. Okay? So now, I've got my w variable, I've got my a variable, I've got my k variable. I should be ready to write our model. Okay? So, next question. Write the model for the writer's height as a function of time. So we're going to have height of time, and it's going to equal, my amplitude was 25, so I've got a, 25, sine. Inside of those parentheses, I'm going to have that pi over 10 times my t, that's a t, okay, for my time, however long I'm on the ride, plus 33. Okay, so now I have a good model. All right, so letter E. Using this model, where is the person when they first get on the ride? Well, when I first get on the ride, my time would be 0. Okay, so let's go ahead and check this out. If I do h of 0, okay, I'm going to have 25 times the sine of pi over 10 times 0, that's got to just be 0, plus 33. Now, if you remember a sine curve and how it looks, the sine, that's a terrible sine curve, my board's off a little bit here. The sine curve at time 0 is at the origin, which means that the sine of 0 is 0, times the 25 is a 0. This person's 33 feet off the ground when they get on the ride? Oh dear, that doesn't really make sense, does it? But that's what our model says. Maybe our model's not quite right. Maybe something needs to be changed about our model, okay? It doesn't really make sense to be 33 feet off the ground when we're trying to get on the ride, okay? So letter F, write a different equation for height that might be a little more realistic in terms of where the rider is when they get on the ride. Okay, so I'm going to take a moment here. I need a little more writing room. And I'll go ahead and copy that model down. We said h of t equals 25 sine, that's a sine, and that was the sine of, I already forgot my b, pi over 10 times t plus 33. Let's just make a quick sketch of this. What does this thing look like? Okay, well, this is my time, and this is my height as a function of time, and I know that the whole thing has been shifted up 33. So if this is 33, this is sort of my midline, if you will, of what's going on, and I know that it takes me 20 seconds to complete one cycle, okay? So in those 20 units from 0 to here on the x-axis, I should be able to complete one sine curve, okay? But I'm starting at 33 feet in the air, and I'm going up another 25 feet, so I'm kind of doing this so that I end at 20, okay? All right, well, that's all well and good, but that doesn't make any sense. What we really want to happen is we really want our height axis, if you will, to be right here so that at time 0, I am getting on at the lowest possible point on the Ferris wheel. Now, there's still going to be a ramp up from the ground, because if there wasn't a ramp up from the ground, then our toes would all drag on the ground, and people would get really mad and hurt, and little kids would be crying. It's not a good thing, okay? So we're still going to be partially off the ground, but what we really want is we want our new y-axis, if you will, to be here, and our x-axis to be there. Okay, so what does that mean? That means that my sine curve got moved. Let me trace my sine curve. All right, so that red sine curve, let's see if I can grab just the red one or the blue one. Let's see. There we go. We want the red sine curve, which is currently right here on the y-axis, to move over to be there. So what just happened? Well, the red one lined up with the blue one by moving left. And how far left did it move? That's the question. So we know we're going to have to go left. Okay? If this is 20, and again, we've got quarters on our graph, the question is, where is that? That's 3 tick marks. Well, if I take 20 and I divide it by 4 tick marks, then each tick mark is 5 units. So I need to move left 3 times 5 units, or I need to move left 15 units. So my new model is going to look like this. H of t equals, we're going to have 25 sine, and we're going to put in a phase shift here. And we want to be careful not to mess up. Remember, factor, factor, factor. So we're going to leave this in factored form, and we're going to go to the left. So transforming to the left, I'm going to use a plus 15, and then our plus 33. Again, we can't move this thing up or down, or else our feet are dry on the ground. So all we're doing is we're going to move the whole graph to the left 15 units. Next idea. Okay, naturalists found that the population of some types of predatory animals may vary periodically with time. Sometimes there's more foxes, sometimes there's less foxes, based on how much food is available and things like that. Okay, so we're going to assume a sinusoid models the population of foxes in a certain forest as a function of the time after the record started being kept. So we'll call the time after the record starting being kept as time 0. Okay, we've got population, and it's going to vary periodically with time. In other words, we've got population as a function of time. Okay, so we're going to have our time here, and this is being measured in years, and we're going to have our population being measured in number of foxes. All right, so if we look at this again, a minimum of 200 foxes appeared. So here's 200 foxes, and that was 2.9 years later. Okay, so 1 year, 2 years, 3 years. Let's make some nice equal size tick marks here. 3 years, 6 years. Okay, 2.9 years, there were 200 foxes. So right about there, a little bit before the 3. And if we keep going, the next maximum occurred a little bit after 5 years, 5.1 years. There were 800 foxes. So 200, 400, 600, we've got 800 foxes over here. And that's going to happen at 5.1. Okay? So 5.1 comma 800. All right, it's modeled by a sinusoid. Now, what we have to recognize is if this dot is the minimum and this dot is the maximum, then the curve is kind of going like that. Okay? It's not one complete cycle. How much of a cycle is it? So 5.1 years, 2.9 years. We're going to subtract those two. We're going to get 2.2 years. So this distance from here to here is going to be 2.1 years. So if I go 2.1 years the other direction, to the left, I should get one whole cycle. Or I could keep going to the right. 2.9 minus 2.1, that's a 0.7. So the first blue mark should be the beginning of the curve. And if it's sinusoid, then the beginning of the curve should also be another maximum. Okay? So we had half the curve given to us, we drew in the other half of the curve, and it looks like now we would be able to write a model. So, about a unit ago, when we first started talking trig, we gave you pictures and we asked you to write the equation of the model. This is very similar. The only difference is they gave me words to create the picture. Now I can take the picture to create the model. And that's exactly what they're asking for us in letter B. Okay, so what do I need for our equation? Well, when we look at this picture, which parent function does that look like? We're going to use this as our starting value for our cosine, and this is our ending value for our cosine. My board's a little bit off, but you're coming right where that blue one is. All right, so 2.2 years was half of my period, which means that my period is going to be 4.4 years. Okay, so just like in the last example, if I know the period, I should be able to work backwards to determine what is that b value that goes in my equation. Okay, so period comes from 2 pi over b, and that is 4.4 years. So if I multiply both sides by b, I'm going to have 2 pi equaling 4.4 times the b. I'm going to divide by my 4.4, like so, and I'm going to get 2 pi over 4.4 equals b. Or if you do a little bit of reduction, b is going to equal pi over 2.2. All right, so now I've got a b value. Yep, that part of the board just doesn't like me. Okay, I got a b value. What else am I going to need? Well, I'm going to need an amplitude. Remember that amplitude is the distance from the middle of the graph, if you will, the midline of the graph, up and down. So what we're going to do is we're going to take half of our maximum minus our minimum. If you don't have this definition written down anywhere, it's a pretty handy one. Half of the max minus the min. Okay? The maximum was 800. The minimum was 200. The difference in those is 600, and half of that is going to be 300. So we simply did this little equation. Okay? Amplitude is 300. Amplitude is our A value. Okay? Now, if I take that amplitude and I count down that much from a maximum, down 300, that would be 500, and up from a minimum, my board's not going to cooperate here. See if I can get that drawn in there at 500. Okay? So that 500 value is that middle, or what used to be the x-axis. Okay? If that's 500, now we know our vertical shift is up 500. Okay? All right, so we've got a vertical shift, which is D, by the way, in the whole ABCD equation. Okay? We've got D is vertical shift is 500. We've got a B value that represents our period. We've got an A value. The only thing that's left is, what is our phase shift? How much did we scoot over to start right there? Well, if you remember, right there is the beginning, and this we decided was the period of 4.4 years. This value we know was 5.1, so if we take 5.1 minus 4.4, we're going to get a 0.7. Our phase shift is 0.7 years. We're ready to write a model. Okay, population of foxes as a function of time is going to equal our amplitude, which is 300. We've got a cosine curve. Okay, we've got a B value of pi over 2.2. We've got a phase shift of 0.7 to the right, and plus 500 for our vertical shift. Alrighty. So far, so good. Okay, well, after we write a model, we usually like to use the model. So what I would do if I were you is I would go ahead and type this into my my Y1 in my graphing calculator, and you could check your model with it, set up the same scale that we already had on our picture. We had from 0 to 6 or so on the x-axis, and we had from 0 to 800, or maybe a little higher than that on the y-axis, and make sure that this model is represented by the picture that you see on your graphing calculator is going to look the same as the picture that you see on this screen right now. Okay? So take the time to do that. Now, once we know that, now we can predict by saying P of 7 years and P of 10 years. Okay, and then we can use the Y1 feature on our calculator to do our prediction. If you go ahead and do that, let's see, my answers on here somewhere. P1 of 7 is going to be 227.110 blah 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 blah. Okay, but these are foxes, the population of foxes. I can't really have 0.11 of a fox. I know we had points of zombies, but these aren't zombies, these are actual critters. So let's go with approximately 227 foxes. Okay, we're going to do the same thing when our value is 10, and when we do our approximate there, we're going to have 726 foxes. Okay, at 10 years. So this thing just keeps oscillating back and forth. Alrighty. So far so good. 2 down. I think there's 1 more left. Okay, last one, sinusoidal regression. Okay, so we've saved you a little bit of time here because I went on and graphed the scatter plot that you should see. So if you're not comfortable making a scatter plot on your graphing calculator after what you did last class plus this video, then you're going to need to stop by and see us, okay? I know some of us didn't have Algebra 2 at our academy, and that's fine, but please stop by so I can show you on your graphing calculator how to do a scatter plot. Okay, we're going to go on with the assumption that you already know how to do that. So, example 3, we have an average discharge rate of the Alabama River. In other words, the Alabama River flows into some other water thing, whether it's another river or the ocean or something like that. And the discharge rate is the amount of water coming out, okay, at the end of the river. So, it's given in the table for the odd numbered months of the year. January is 1, February, March would be 3, etc. so forth, okay? November would be 11, you get the idea. And the window that I've chosen for the scatter plot is given here, okay? So it's given to be 0 to 12 on the x, and it's given to be 0 to 2000 on the y, okay? So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, okay? You get the idea. And then to 2000 on the y. So if this is 2000 up here, then we're probably counting by 200s, 2, 4, 6, 8, yep, this would be 1,000. Okay, so there's our picture. And we're going to go ahead and graph, we're going to find a sinusoid regression model. Okay, so let's pull up our graphing calculator. And I already have the data typed into stat, I believe. Okay, same data that you see there. And I already have my scatter plot going, sorry. We're going to go to stat now. We're going to calculate, and again, just where we found linear regression, we found quadratic already. We've done some logarithmic. If you keep going down, I don't remember what number it is, so I have to arrow down every time. And we're looking for sine regression. Again, why is there no cosine? You should be able to answer that question right now. Okay, so we're going to do a sine regression, and we've got our list 1 and our list 2, and then we're going to store that in our y1. Okay? And again, notice that on the sine regression, it's going to give you sine of bx plus c. Now that's not the same a, b, and c, b and c rather, that we used on the last example. They have the b value factored in already, so just be careful. They give you the model, you just copy it down from the screen. In fact, if you do that, it should look like this. Now we can round our model to the thousands, but when we go to use it, we want to make sure it's stored in y1 so that we're not rounding it. Okay, what is this sine curve going to look like on top of our equation? Well, it'll graph it for you. Looks something like that. This always feels like a game, try to hit the dots. Okay, so now we have our sine curve. Okay, you can go ahead and copy that onto the model that was given. Alrighty, so we've got our sine curve coming through like that. You can see my board's off a little bit. Okay, letter B. Assuming the model continues for the next calendar year, estimate the flow rate for the following June. Okay, so first question, what month number is June? January, February, March, April, May, June. I picked June, I like June. Okay, June is the 6th month of the year, but this is the 6th month of the year after all these months. So a year has gone by. So we're going to actually do f of 18. There we go. If you go back to your home screen, let's see if this one has the right operating system. We're going to go alpha F4, and it recalls all your y values for you. So you can go y1 of 18 years. And we get 939.257. Now, can we have 0.257? Is it okay to have a decimal this time? Well, what are we measuring? We're measuring water. Can I have decimals of water? Of course I can. In fact, this water is flowing at a rate of cubic meters per second. So again, if they give me units, I'm going to give them units back. So there's the answer to that one. Okay, let's close that down. I think I might have one more question here. All right, last part of the example, letter C. This time we're going to use the graph and the equation to estimate, okay, the number of days per year when the flow is below 500. Okay, below 500. So where's 500? First of all, the flow rate is graphed on the y-axis here. Okay, this is my rate. And we're going to go 200, 400, 600. So 500 is going to be a little higher than that. Yeah, right about there. Okay, should be right in between the 400 and 600. My board's off just a little bit. I've been complaining about that all day, haven't I? I think I can, there we go. Now it's at 500. Okay, so what we want to do is we want to estimate the number of days per year that the flow rate is below that amount. So we're talking about the curve over here, okay? So we've got this x value and this x value, and I want to know how many units are between. Well, if I check, this would be 1 day, 2 days, 3 days. Looks like about 3.5 days. So if the flow rate's I'm sorry, not days. What's the units on our, go away. What are the units on our x-axis? Well, it was time, and time was being measured in months, not years, months. So we don't have 3.5 days. We have 3.5 months. So how are we going to reconcile that? Well, we'll have to approximate how many days are in a month. So we'll go with 30 because that's right in the middle. Pretty close. Okay? And we're going to get about 105 days of the year that our flow rate is below 500 cubic meters? Yeah, cubic meters per second. All right. If that question had not said estimate but find, then you could use your graphing calculator to find the intersection points right here and then subtract them to find the difference here. And again, you'd have to approximate how many days in a month where that information would be given to you. All right, that'll about do it for sinusoidal modeling and regressions, and I will see you in class.